I am blue box. Anybody have questions out there? Holy macaronis. No, you guys are everything going good? Yeah? Doing chapter 7 homework. It's going awesome. Kick ass. All right. Has everybody had a chance to look at your quizzes? Is there any questions from those? No? Okay. Neat. Oh, here we go. I tried to. Yeah, if you think so, let me check. Somebody's asking me a specific question. So there were people that got the bonus questions correct. So I definitely was including that in the grade. Let me double check. Let me see. Did I look at yours? Oh no, did I not even look at this, Jeff? Well, that's not right. Okay, that's not right. So person that chatted to me about the bonus, I think I might not even have looked at it. I got to look at your specific quiz. You might have gotten the second one right. So don't let me forget about that. Shoot me an email right now and say, hey, look at the bonus, math boy. Maybe don't say math boy. I don't care. Second bonus from the, oh, you're asking how to do the second bonus. All right, let me look at that. What was that one? Bum, bum. Oh yeah, that was the, that was actually a pretty, well, let me not, well, yeah, it was a pretty straightforward one. You just have to know, you just had to remember the model for it. Let me see, hold on. All right. So the second bonus was the one that said something like the half-life of a substance is so many days. After so many days, it's been reduced to this. Yeah, so, oh, you didn't do it. Oh, okay. I saw the comments for my quiz, but there was no grade for it. Oh, okay. I'm still considering what to do in that situation, person. I got your reply. I got to consider what to do about it. Yeah, and again, so the other person just email me if you haven't done so yet. The person talking about the bonus points. Remind me. Somehow I think I didn't even look at them on yours, so I'm sorry. There should be marks on the bonus if you tried them. If there aren't, I might not have looked at them. So past Jeff was just like, whatever. So you got to excuse past Jeff. All right. I'm not sure. Somebody asked me a question about a bonus, but they didn't even do it anyway. So I'm not sure what to do with that. I'm not going to tell you anything if you didn't even try it. Anyway, so it's one of those where you solve for K from the information I gave you. And then you can figure back out how much there was at the beginning. Anyway, so that's why it was bonus. Anything else, guys? Everybody else okay? Okay, all right. I do need to talk about something. There was at least one person that I believe, allegedly, I know 100% for sure, but I'll say officially, I'll say allegedly, used something called photomath. Have you guys heard of that, photomath? It's probably a better place to be. You can point your phone at a problem and it does it for you. It shows all the steps. Before you get all excited, it does many, many problems in a very strange way. And it's very easy for me to pick up on that's what was done. Is everybody with me? So there's a multitude of ways to get answers instead of from your own head and work. I know a lot of places to check for that. In fact, the math department pretty much shares with each other, has an updated list of places to go to check. I know there's a subreddit on Reddit called Cheat at Math Homework. That's always neat. I frequent that. There's some other subreddits on Reddit that I keep an eye on. There's Chegg. You can write to Chegg and get answers. But that takes time. Those kind of things take time. So that's why I like the time limit on the quiz. Anyway, I was talking to somebody earlier about trying to find the balance as a teacher between being a hard ass enough so you can catch the cheaters and you can prevent cheating, but not being so hard ass that you implement things that make it hard for people that aren't going to cheat. Does that make sense? So I don't want to make things more difficult for people when the math is difficult enough and they're never going to cheat anyway. And a lot of these things are very good. Photomath is really good for checking your work and stuff, but unfortunately it's not used that way. People just copy it even though they don't understand what it's saying, and that's not good. All right, so at least one person was doing that. Any other questions from the quiz or from homework?
I do have a question about 4C on the quiz. I noticed you added a lot more of things that we've learned in the past in this quiz too. So I had some trouble with that one.
So are you talking about the point where it becomes this interesting thing you have to factor?
Yeah.
Oh yeah. So I like the way you said that, but to be honest, it isn't necessarily a conscious decision. It's just, that's what happens with these problems, right? That's just how these problems are going to go sometimes. So the way I created everybody's 4C is I picked a value of X. And then, so like I made X3. So then I made a logarithm of X minus 2. That would be log of 1, which is 0. Do you kind of see what I'm saying? So very often I didn't even consider what it was going to look like because it didn't matter, because we all have to know how to factor. So who gives a shit? But you bring up a very good point. Every damn thing you've ever learned can come up at any moment. That's not... if that doesn't cause you some anxiety, but I'm sorry, it's the truth. But don't overly freak out about that. I do sort of keep an eye on it to a point. I want to make it a little more focused, but there will be things like that will definitely just come back up, because it's sort of like, knowing order of operations. That's always there. So factoring is sort of like on that level for us now, almost, where it's just, that's an automatic. Somewhere is going to be factoring. Anything else, guys, from quiz or homework?
So you're not going to help show me out, like, the factoring part of that?
All
C?
right. Everybody's 4C should have come out to one of those trinomials with a number that's not 1 at the front. Right? Let me spotlight me, because it's all about me. So let me see if I just make one up. I should be lucky enough to not make one up that somebody had. I know. Hold on. I gotta adjust. So if I had something like, here's my go-to. I know this one works. So if I had this, and in fact, it would have been something more like this. Now, what really gets me down, real quick, before I do this, if I have a problem like this, can I just do this shit here? I basically gave it away with how I said that. Is that a good next step? Why not?
Because there's a multitude of answers X could be to multiply itself.
There's an infinite number of things each of these could be to make 8. There is 4, 2, 1, 8, 16, 1/2, 40, 1/5. Square root of 8? Square root of 8. I mean, holy shit. Maybe? No? So, hell no. What's the only number that can be here that I can do something with?
0.
0. All right, that's number 1. So I saw a few people do this kind of thing, which is sort of like a Math 90 student saying 4 times 2 is 6. So no good. So I got to subtract 5 first. Now, how the shit do you factor this thing? Now, of course, you always have quadratic formula, which would kind of make me sad, but it still works. But how do I factor this? Does this seem familiar? And then you find factors of that make that, and then you can break up the middle term. And then you can group. Yeah, blah, 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 blah. Yep. Is that all right? I like it. Now, you know, like I said, you could use quadratic formula here. I'm not going to take points off if you do. I am going to shed like half a tier that you didn't even try to factor it if you do that. But okay, maybe 2/5 of a tier. I would cry. Anyway.
Got it. I reviewed it and I see what I could have done differently. So thanks.
Sure. How's everybody else? Anything else, guys, before we get back into other stuff?
When is the next quiz?
It's funny you say that. I was about to check right now. I think officially it's supposed to be, yeah, supposedly it is this Thursday. Which I see no reason we can't keep it there because we are done with chapter 7. I was going to say a few more things about chapter 7. And then we're going to move into chapter 8. Unless people have questions from chapter 7 homework, in which case I could spend a little more time in chapter 7. So officially the next quiz is still this Thursday on chapter 7 because we are done with chapter 7. Okay. There are, I do want to make at least one point before we move out of chapter 7. Maybe we'll do a couple example problems because I feel like there should be more questions right now. One thing I want to really make sure you understand, I kind of made this point too early, but now that we've talked about some more things, I can make this point again. When an angle is inside of a sine or a cosine or inside of some trig function, it does not matter if it's radians or degrees or whatever, to be honest, as long as I know what the sine of that angle is. When theta is not inside, like it is for area, theta is not inside of a trig function, it must be the real measurement, the physical measurement, the number that represents something real, which would be radians. Which is why, as you progress, you normally kind of naturally start using radians all the time so you don't make a silly mistake, because then it works no matter if it's in or out. It works. Okay, and why does that make sense? Because if I said sine, and then I described an angle, sine of the angle that looks like this, I can even use words in here, because sine of the angle that looks like that, what is that? But what is that gonna, does anybody know what that is? What's the answer? What's the sine of that kind of an angle?
90 degrees or pi.
All right, that's what it is. So what's the sine of it? Who's got that memorized? Sorry?
Is it y over x?
Is it 1?
It's 1. So I wasn't asking for a definition of the trig function. I want to know what sine of 90 degrees is, right? Why is sine of 90 1? Who can explain that to me? You're like, I don't know, man. You get paid bucks to explain shit, not me. Sorry. I'll say what's in somebody's mind. But still, you know, oh well, you're in my class. Do what I say. Why? Can somebody explain to me why that makes sense? What is sine like?
Sine likes y.
Sine likes y. And at a 90-degree angle, it's all y. So that's why it's 1. So at 90, it's all on the y-axis. So sine is 1. So let's do this. I want you guys to take a minute, figure out, we did this last time, but you should be doing this for yourself. I think I've made it clear how important this is. Can you tell me what the cosine of 60 degrees is without doing much work? Can you tell me? Just do this on your own. Do this real quick. What do you got, Jim? I don't know, man. All right, so do those 3 without using a calculator, without any of that kind of shit. Oh, yeah. Somebody saying they're late because they thought today was a holiday. I understand. That is the optimistic part of your brain. 2020 is shrinking that parts of our brain, I'll tell you. It's not a bad idea. This one's in the first quadrant. It's not a bad idea to draw these out and identify the reference angle. In fact, on a quiz, I will very often ask to see this because it helps you if I ask you to do this. It's the same thing here. So this one you just have to know. But I don't know how to ask this. Did anybody just straight up, or did you already do this or planning to straight up memorize this shit? Like memorize sine 30 and sine 45? I mean, it's fine if you do. That would drive me insane. And if somebody else has a different way of looking at things, let me know. But to me, what makes the most sense is sine likes y, cosine likes x. Cosine will get smaller and smaller the closer it gets to nothing but y, the closer it gets to 90 or 270, the ones that are on the y-axis. So that is close to 90. So the answer should be the smaller value it can have. And what's that?
1/2.
1/2. I love it. This one, what's the reference angle?
45 degrees.
45 degrees. And what kicks ass about tangent at 45
Tangent is 1.
Yeah, because sine and cosine are equal and tangent is their ratio. Kick ass, kick ass. Last thing, is it one or positive 1 or negative?
Negative.
Negative, because it's in the quadrant where x is negative, which means cosine is negative, y is positive, which means sine is positive. All right. So I know it took me a while to say, but if you just think about it for about 8 seconds, you got it. And I'd much rather do that than take up what limited space I have left in my brain to memorize this shit. This guy, what is the reference angle going to be?
30.
Yeah, I love it. So it's pi over 6 short of a full pi, which is 30. I love it. So this will equal, and secant, that almost doesn't matter, but what is secant related to? Cosine or sine?
Cosine?
Cosine. S goes to C. C goes to S. I love it. So that's related to cosine. And what's cosine going to be in this quadrant? Positive or negative?
Negative.
Negative. And like you said, that's 30. So you can take this with this and rewrite it like that. So now it's -1 over, and what's cosine of 30?
Square root of 3 divided by
Good. Because that's closer to the x-axis. Cosine should be the bigger value. Rad 3 over 2, which is -2 rad 3, which is -2 rad 3 over 3. Well, just got to rationalize that bad boy. Let me stop for a minute. All right. So the reason I love sine likes y, cosine likes x, because it keeps in your brain why the values it takes on make sense. They're not just something to memorize. Sine is the y piece of the triangle. What's really weird when I'm at 90 degrees, the triangle is a line where the x part has no width. That's why cosine of 90 is 0. It's got no x piece to it. So I can have a triangle that one side keeps getting smaller and smaller and smaller until it's a line. So how big is that side going to be? 0. Okay.
Can you explain where you got the 30 from?
Yeah, pi over 6. What's pi in degrees? Pi is equal to how many degrees?
90.
180. And 180 divided by 6 is 30.
Got it. Thanks.
So you want to pi over 6, pi over 4, pi over 3, pi over 2. See how it's getting bigger and bigger because I'm dividing by less and less? So that's 30, 45, 60, 90. Does that make sense? No? Yes?
Yeah, that makes sense. Thank you.
Sure. All right. So this is the kind of problem you should just want, because you can eat this up. You can put it, and then eventually get to a point where you've got this memorized. Somehow, up to you to figure out how you want to memorize that stuff. Okay. Let me think. There was another thing, was there? I can't remember. I don't think there was much else. No. Oh, I'll remind you about a couple things that we did last time. Oh, there are a couple of those. I like that. Let's do a couple problems out of 7-4, and I'll remind you about this first. Erase all this stuff. So last time we determined the Pythagorean, get out of there. Identities. Shot. Sine squared plus cosine squared equals 1. Then if you divide by sine squared, you get 1 plus cotangent squared equals cosecant squared.
But if you divide by cosine squared instead, you get tangent squared become a tangent. Plus 1 is divided by sine, divided by cosine squared, so that would be secant squared. So you have to memorize these, which means you have to memorize this, because you can build these off of that. Plus co, no co. Now, on the heels of this, I want to show you that animation that I put up on Canvas, because it's really funkydelic. I learned something I never learned, which is really kick-ass. I have no idea if anybody's looked at this yet, but just watch this for a minute. There should be some things in here that are obviously things we know. And then there's other things that, you know, I had the same reaction you do, which is, what the hell's that? All right, so as you watch this, inside it makes sense. See, cosine is the x piece, sine is the y piece. I mean, yeah, sine is the y piece, cosine is the x piece. Right, the radius is always 1 in this unit circle. They chose tangent to be represented in a different way, but that's actually, there's multiple ways you can represent it, to be honest. But I want you to notice something. Let me see, where's a good place to stop it? Maybe there. I want you to notice something interesting. Maybe this is not the best. Where do I want it? Let's put it in the first quadrant so it's maybe easier to see. Yeah. Stop. Okay. So this is secant right here. See that? This whole thing is secant. This side of this. Do you see this little triangle here? So one side is 1, one side is tangent, and this side is secant, right? You guys with me? And the right angle is right there. So then secant is the hypotenuse of the triangle. So let me let that sink in. Oh, I can blow this thing up. Oh, look at that. That's better, Jeff. Jeff is learning. All right. Sorry. He's learning. Watch out. So I got a triangle right here. It's a right triangle. The right angle's right there. Right there. Anyway, all right. This is secant. They just put it down there just so it's, because there's already a lot of shit here. So they want to just put it down there. This is 1, this is tangent. So 1 squared plus tangent squared equals secant squared. Right? Yeah, and then you can see the other ones up there too, which is kind of nifty. But real quick, is anybody, so the very first thing I saw when I found this animation was versine x cusk. What the shit? So I looked down here, versine, coversine, x secant, x cosecant. It's like, what are they now? They used to be a cosecant. So I had to search this, and it's something that hasn't been used since the 1800s or something insane. Anyway, so that was exciting to me because I had never heard about this stuff before, but oh well. So that's all I want to say about this. Go away, stop it. And that's up on Canvas. If you want to access that animation, just sit there and watch it for hours on end. I don't know. Might be more interesting watch it when you're high. Might be safer to watch that when you're high. I don't know. Help you come down. Somebody just left. They're like, I can't believe he's talking about. Anyway, sorry. Oh, this is something we're going to do later. I don't want to show you that yet. All right, so coming back to this, I do want to do a couple of problems. Where are you? No. Really? Oh, they just have a couple here. Yeah, okay. There's something coming our way that we don't really know enough yet. It's called either simplifying trig functions or verifying trig identities. So look at number 70, for example. Is there a way to simplify that expression?
Yes,
How?
because cosecant is 1 over sine.
Good.
And tangent is sine over cosine. So you
Good.
can
1 over sine, sine over cosine. Go ahead, sorry.
So you can cancel the sines.
And then you end up with what?
1 over cosine, so
Which is
secant.
secant. Kick ass. So cosecant times tangent is secant.
That's funkadelic. How many of those exist? Oh my God, an infinite number. You're gonna be, you'll be a combination of amazed and horrified at how many identities we can create, and the fact that we're going to try to prove some of them. It's going to be exciting, something to look forward to. These are very simple. One of your primary things, if you see something that says verify this identity or simplify these trig expressions, the first thing you try to do is write everything in terms of sine and cosine, just like somebody just did. I didn't even see who it was that I was talking to. I'm sorry. That's the first thing to try. And if that doesn't work, then you start trying some of these out. That's the next level of what to try in this kind of problem. So we're going to see a lot more of these coming our way soon. Okay, what was the other? I know there was something else and I can't remember. Something else I wanted to do before I left this chapter. I cannot remember. Too bad for you, Jeff. All right, I'll stop. All right, let me check one thing out real quick. I'm not going to remember what it was, am I? No, you're not, Jeff. Oh, well, we'll see when you hit it in the homework. We'll see if people have questions. Yeah, that's it. All right, so if there's no questions, I'm going to get into chapter 8 now, like a madman. Okay, here we go. So what we're about to do, we know what sine and cosine represent. We know how to calculate them for certain values, so forth. But we haven't, believe it or not, we have not graphed them yet. We haven't graphed the functions themselves. We can find them in a unit circle. We can find the sides they talk about, but that's not a graph of the function itself. A graph of a function is inputs, outputs for that function. That is not what the unit circle is. Okay, I like it. So what we're going to do, what I want you to do actually, because I'm lazy. Let's start by graphing sine theta. So let's do it. This won't be too bad. So let's do 0, pi over 6, pi over 4, pi over 3, pi over 2. Put the values. I should have gotten a bigger freaking. Oh well, Jeff. Next time. Well, let's just do this first. Fill these in. Learn how to use your space, Jeff. I'm gonna. All right, I'll move that over there so I get some room. All right. So what's sine of 0?
0.
0. Because at 0 degrees on the unit circle, it ain't no part of y. It's all x. The sine is unhappy. And then what? And then of course I showed you that neat progression. I don't know if you guys remember. It goes square root of 1 over 2. So this will be, oh, it doesn't, Jeff. Yes, it does. So this is going to be 1/2, square root of 2 over 2, square root of 3 over 2, square root of 4 over 2, which is 1. You guys remember that? Maybe. That's really useful. That's mostly useful when you're going to graph the trig functions, if you remember those. And I put the negatives in there also. What happens when I go this way? What happens to the sine values for negative?
They turn negative.
They turn negative because sine likes y and y is negative in that quadrant. So it's going to be negative of what it was over there. I like it. And I really don't have to do more than this. How many more, how much longer could I do this? Like I could do 2 pi over 3 and 3 pi over 4 and 5 pi over 6. And how much longer could I do that for? Oh, I will in a second. Let me see. How much longer could I make tables like this? I don't know. That might be a weird question. Huh? Forever, right? 500 pi over 3, that exists. 18 billion pi over 4, that exists. I mean, do you guys understand what I'm saying? So, real quick. If any of you get to Calc 3, maybe before then, I can't remember off the top of my head. Angles are boring in that they start to repeat at 2 pi, but they repeat even before that. Is everybody kind of with the trig functions of angles, right? So it's kind of like once you make the circle, it just keeps making the circle, right? It's time to make the cookies. I already made the cookies. Oh my God. But when you learn about 3-dimensional, so if you add in another dimension, what it will do then is it makes a circle and it comes out. So if I have another dimension, you can make a spring. It keeps drawing a circle, but it moves away from the board maybe 1 step every time. Does that make any sense? That gets more interesting. Then it's like a very long parking, getting out of a parking garage by doing one of those turny deals, right? Corkscrew things. Okay. Enough of that shit. None of that shit's about to happen. So don't forget. So what I'm going to do, my scale is going to be a little bit freaky, so I'm going to have to improvise here a little bit. So I'm going to do, so here's my pi over 4, pi over 2. So pi over 3 is going to be in here. Pi over 6 is going to be in, what am I thinking? Pi over 6 is going to be in here. Pi over 3 is going to be in here. There it is, Jeff. You can do it, buddy. The scale sucks. Too bad. The interesting thing about sine, the outputs for sine are in between what 2 values? What's the smallest sine can be? What's the biggest sine can be?
-1 and 1.
-1 and 1, exactly. Because it's optimal when it's on the y-axis. So it's either 1 or -1. That is the biggest and smallest sine can be. Same thing is true for cosine. So 0, 0. Let's put 1, -1. Pi over 6 is -1/2. And that's negative pi over 6. You put your positive over here. Pi over 6 is 1/2. So that's about right there, maybe. And then pi over 4 is √2 over 2. What is √2 over 2? √2 is 1.4 divided by 2 is 0.7. So that's going to be a little bit up there. √3 over 2, I always forget what √3 is. Is √3 like 1.7? 1.7 something, so it's it sounds right. So it's 0.8. So pi over 3 is in the middle of these two somewhere. 0.8. Pi over 2 is 1. So I've got it going like this. Become big, become big, become big. And then back here, you pretty much can see, I'm not going to graph every single one of these now. Is everybody cool that rad 2 is 1.414, blah, blah, blah. So half of that is 0.7. So negative 0.7 at rad 4. I mean, pi over 4. And then at pi over 2, it's negative 1. And what it's going to do, my scale sucks, but oh well, is it's going to just keep going like this. It's just going to keep going and going and repeating these values. And you know this is true. You make this a little bit better. Because as you move, sine grows to the tallest, its highest value, and then it shrinks the same way back to 0. So it grows, and then it shrinks, and then it grows negative, and then it goes back to 0, and then it kind of just keeps repeating. So this is a really nifty pattern. I've got an animation for this, which is neat. So it's just going to keep going this way forever. What's the next time it's going to hit the x-axis? Let's see if you guys can figure that out. When is sine 0 again? After 0.
Pi.
Pi.
Pi, I love it. So at pi, which has almost a good scale, it's going to be 0 again. And then it's going to keep going. Then it's just going to repeat. Repeat and repeat. And this is just going to keep going, repeat. So that's your sine wave. That's your wow. I like it. Let me stop for a minute. It's because it's a circle and never ending. Exactly. Oh, I'm sorry. I missed somebody's. So this, all right. So somebody's asking me, how did I get this value? All right. Wait, I have a question. Can sine ever start from 1? The unshifted sine graph will be this. End of story. Notice what I just said. Isn't sine a function? Is this a function? Why?
Passes a vertical line test, right?
Passes the vertical line test. Kick-ass. Is it a one-to-one function?
No.
No, because it does not pass the
Horizontal line test.
horizontal line test. Thank you. So this is a function. I've already forgotten what my point about that was. What was somebody's question? Oh, it is a function. And even if it wasn't a function, I could still do transformations. So you know that's going to be the next thing we talk about. We're going to talk about the basic shapes of the graphs and how they look and where they start and all that kind of stuff. But then we're going to start moving these suckers around and compressing them and shit. And going this way makes more sense now because compression makes sense when you're talking about a spring. And this sort of looks like a spring. If I compress it, it looks like a spring that's getting compressed. I mean, it makes sense. Oh, that's all right, man. Somebody keeps getting disconnected. It just sucks on your end. Sorry. Oh, okay. So coming back to this. All right, what part of this I'm gonna take this away. I never want you guys to forget. You really have to not buy into isn't really the right, but do you guys remember how I drew an equilateral triangle? And then we cut it in half, right? And I was like, this is 1. All the sides were 1, so this is 1/2. Do you guys remember this, the time we did this? And since it was equilateral, that's 60, and that's half of 60, that's 30. So there's your 30, 60, 90. Or your pi over 6, pi over 3, pi over 2. And since I know these two, I know that this is rad, if I use Pythagorean theorem, this is rad 3 over 2. So sine of 30 is 1/2 over 1 is 1/2. Okay, I like it. It's not necessarily a good idea to have this in your head all the damn time. But if you ever feel yourself getting disconnected from why this is true, you do. One of my instructors is an Australian dude who taught nuclear physics. And his favorite saying was, go back to basics. I can't do Australian, obviously, very well. But he would say, Jeff, go back. He would say, go back to fundamentals. That's what it was. Go back to fundamentals. This is the guy that poured liquid helium into his, was it liquid helium? Into his hand. And we're all like, please stop. Please don't do that. It's getting cold. It's getting, like, stop. I'm sorry. All right. So that was a good question. Never lose touch with why that's true. Another way to look at that is sine is the y piece. If I'm only gone up by 30 degrees, the y piece is not very big yet. So that's why it keeps getting bigger and bigger, because now the y piece keeps getting bigger and bigger as I move along. That doesn't explain why it's exactly 1/2, but it explains why it has this pattern to it. That explains why it's exactly 1/2. Okay. So how is cosine going to be related to this? What's cosine going to look like? Let's see if we do cosine without making a table of x. Let's just attack cosine head on. Let me see if I got enough room here. Red. Come here, blue. Yeah, let's just do this. Let's just do pi over 4, pi over 2. All right. So what is cosine of 0?
Isn't it just 1?
Kick ass. So I'm sorry, Brian, I never really did, and I just called you out on this, even though you're private chatting me, I'm sorry. If I shift them, I can make them start wherever the hell I want to. That's the answer to your question, right? Unshifted, they have to, hello?
Cool, thank you.
Okay. So unshifted cosine will always start here. What's cosine of pi over 4?
Root 2 over 2.
Yeah, which is about 0.7, which is going to be about right there. What's cosine of pi over 2?
Zero.
0. I love it, because when it's at 90 degrees, there ain't no x piece to that. So the cosine don't like it. And then this is going to be, what angle would this be? Pi over 4, pi over 2. I love this question. What angle would that be? The next one, using the same scale.
Wouldn't that be pi?
No,
Is 3 pi over 4?
3 pi over 4. So 1 pi over 4, 2 pi over 4. So 3 pi over 4. And that would be that value just negative. Is that cool? Because what quadrant? Isn't that the 90? So any more further, I'm in the second quadrant, it's going to be the negative value. So that's going to be down here. And you start to see this. So what's it going to do back here? What's cosine of negative pi over 4? So whatever cosine is here, isn't it going to be the exact same value there? Do you guys see that? Exact same value. So that's going to be like a mirror image. That seems like it has some kind of a symmetry, like we talked about before. What's my scale doing? Oh well. So it looks like, let's see if I can do this nicely enough. You could do it, Jeff. You still can do it. Can you do it? Really? So it's going to come in like that. Here's -1. So eventually it's going to get to -1. It's going to keep going. Blah, blah, blah. You shouldn't be turning around yet, Jeff. What kind of a scale is this? Where's it going to get to -1? Where's it going to get to -1? Where's cosine of what is -1?
Pi.
Pi. So a pi is where it should get to -1, and then it keeps going. So it actually has this, see how it's this, shifted back by 90 degrees. And that actually is, I can't remember where they put this in the book, but sine of theta is equal to cosine of 90 minus theta. But we've talked about that relationship before, haven't we? I'm pretty sure we did. It's like sine of 30 is equal to cosine of 90 minus 30 is equal to cosine of 60. We've talked about that relationship before. They have a symmetry to them. So the graph should have a connection. And one is the graph of the other one shifted back. To be honest, this doesn't look like it does what it's supposed to. Let me show you what this really is. So it's a shift back and it's a reflection. So there's a couple things happening. I'm sorry, not shift back, but shift forward and then a reflection. Yeah. I know that's a lot of freaky shit. So it's actually a shift forward by 90 degrees and then a reflection. That's how you get that. That's what that really shows. All right, maybe. Okay, that's enough of that joke. So let's talk about tangent. And then I want to show you the animation. Yeah, because I think the animation has all three of these bad boys on it. So what is it about tangent that's going to make its graph a little bit freaky? What is tangent defined to be? Not in terms of sides of triangles, but in terms of other trig functions. What is tangent in terms of sine and cosine?
Isn't it sine theta divided by cosine theta?
I love it. So will tangent have any vertical asymptotes? All right, stop. Either I need less of something or I need more of something, and I'm sorry. Where is tangent going to have vertical asymptotes? What defines vertical asymptotes? Where what?
When cosine is 0.
Yeah, in general, it's when I have something is not allowed in the domain. So since it's the ratio, there will be a vertical asymptote everywhere cosine is 0. When is cosine 0?
When sine is 1? Or when the angle is 90 or 270?
So let's write it in some radians. So when theta is pi over 2, or 3 pi over 2, or 5 pi over 2, or, so how long would that take me? And then I'm not even done yet because it's plus or minus, right? You guys with me? So what's another way to write that? Is there a better way to write that? Maybe not. Nobody? Does anybody have a better way to write that? No? So here's one way you can write it. Let me see if you guys like this. Actually, I can make it even better. What the shit does that mean, Jeff? Well, what's true? Can somebody point out to me what's always true? It's always over 2, right? Makes sense because it's going to have to be at those halfway points. But what are the top coefficients? 1, 3, 5. They are the
Odd numbers?
yes. Ooh, I like it. And how do I write all the odd numbers? 2k plus 1, where k is an integer. I don't know if anybody's ever has anybody ever seen that before? I mean, that's how you write all odd numbers. It's 2k plus 1. How do I write all even numbers?
Just 2k?
2k. Chickens in the ass. All right. This is going to become very important when we get to the part where we start solving equations with trig functions in them. because you know we're going to do everything we've ever done with any function. We're going to do them with these new functions. Right? We talk about domain, range, we talk about graphing them, we talk about values of them, and then we talk about solving equations with them in it, which means we're going to have to know eventually inverse functions of them, which is weird because, for example, isn't sine like, is that invertible? Is that invertible, this function?
No.
No, but I can chop. Now, is that invertible? All right, so that's coming. That's in our future. When I say something, I have to keep going with it. It's just how I am. But that's in our future. So I'm going to have to, just like we did with parabolas, I'm going to have to restrict the domain on each trig function so I can invert them. All right. So how does this really help me? I don't know. So I know there's going to be vertical asymptotes. Let's just do a few cycles. Not even a few. Let's just do one. So there's going to be a vertical asymptote there, vertical asymptote there, vertical asymptote there. All right. And so forth. Both directions correct. So let's do this. What is tangent of 0?
Zero?
0. Keep yes, because it's sine of 0 over cos, so 0 over 1. So it's 0. What is tangent of pi over 4? Pi over 4 kicks ass with tangent, right? Because that's where sine and cosine are. Man, you should turn the other way. So much better.
They're equals, so that would be 1, wouldn't it?
Yes, good. That's 1. Well, that really changed things, didn't it? And what about negative pi over 4? My scale sucks. Negative pi over 4, it would be
Negative 1.
negative 1. Kick ass. So look what's happening. And here's the neat thing. Let me see. How do I want to say this? As I approach pi over 2, what is happening to cosine? It's getting
smaller.
smaller, but it's always positive here, right? So I'm going to go this way. I'm going to go that way first. So the ratio is, since the bottom is going to 0, but they're both positive the whole time, this would be going to infinity. So it's going to go, let me see if I can just keep this to infinity, right? Come on, Jeff. You suck. My scale is killing me. I got to go from this way. That's the only way I can do this. And on the other side, it's obviously going to go to negative infinity, because as I go this way, cosine's positive, but sine is negative. So the ratio is going to be negative, and the bottom's getting closer and closer to 0, so the whole thing's going to negative infinity. And it ends up looking like a cubic. All right, that's not horrible. It ends up looking like x cubed, which is interesting, except x cubed would have kept going forever over. This has got a wall there. So what happens here is the whole image repeats again, because it goes through the cycle again. So something I didn't point out earlier, which I'm kicking myself in the ass for right now, is I didn't point out the idea of how long is a cycle for. So this is called, do you see, so a cycle is how long it takes for it to complete a picture that then is repeated. So a cycle would be from here to there, because that's the complete picture that gets repeated. So and the name for that, the actual name for that is the period. The period is the length it requires to make a full image that is then the part that's repeated. So what is the period for tangent? How long is this?
Pi.
Pi. I love it. And if you remember, the period for something like sine, right? This is 0. Sine is 0 again at pi, and is 0 again at negative pi. So that's a complete image, and it took 2 pi. So the period for sine and cosine is 2 pi. So the period for tangent is pi. So obviously, I think you would agree, cotangent's also pi. It's going to look very much the same except inverted. And the period for sine and cosine are 2 pi. So does everybody understand what the period is? It's how long does it take for it to go through one cycle, and the cycle is how long does it take to make an image that's then repeated. So it's got to go all the way through this. Now it's just going to repeat that forever. So it's 2 pi. Okay. Maybe. The time we got. Wow, time flies. So how's cotangent going to be different? And this will be the last thing we do. Ever. No, I mean, it's for tonight. How's cotangent different? Well, what's the cotangent defined to be?
It's 1 over tangent.
Which is cosine over sine. Is that cool? So where would they be vertical asymptotes when sine is 0? And when is sine 0?
0.
0. I like it. And
Pi.
pi, plus or minus, and
2 pi.
2 pi, plus or minus. So a quicker way to say that, let's see if you guys get this. So if k are all the integers, so it takes on the values of the integers 1 and so k is 1, it's 1 pi. K is 2, it's 2 pi. So this would just be k. You ready for this? Where k is an element of the integers. Oh shit! The symbol right there is the integers. Sort of like big ass R with 2 spines is real numbers, right? Z, well, let's see. Sometimes you see it with 2 spines too, but Z is the integers, or like one of my teachers said, Z. Z. So that's not going to be the only difference for cotangent compared to tangent. So let's try to trace this bad boy out. I'm going to take this away. Let me put in my vertical asymptotes. Where am I at? Wait. So let's do pi over 2 pi. Do I want that? Do I want? Doesn't matter. So here's 0. It's going to be at 0. And that pi. And that negative pi. And then forever in both directions, right? So you might think it's going to be like this, but let's double check. What is cotangent of pi over 4? What quadrant is that in? So that's going to be right here, right? What is cotangent of pi over 4? It's going to be positive or negative. And this is the nice one. It doesn't matter if it's cotangent or tangent. What kicks ass about pi over 4? As always. That's where sine and cosine are
Equal.
equal. Cotangent is a ratio of the two. It makes them go the other way around, but who gives a shit? They're both the same. So cotangent of pi over 4 is
1.
1. Positive 1. Right? Cotangent of pi over 2 would be what? It's cosine over sine. What's cosine of pi over 2? Cosine of 90.
0.
0 over 1, so you get 0 there. And then you can imagine what this will be. It'll be another 45-degree angle, but now I'm in the second quadrant. I really want you guys with me as I do. I'm in the second quadrant now, which means whatever it was over there, it's going to be the negative of that because cosine of negative sine's positive. So that's going to be -1. So do you see what happened to the image then? It's not just moved over, it's also reflected. So that is what that looks like. Oh shit, I went over. Too bad. So it looks like this repeated forever in both directions. And again, you can see that the period is pi. So let me show you 2 things and then we'll call it a night. I'm going to show you the animation I talked about. Why did you do cotangent, but it didn't? So we still have to do cosecant and secant. But I do want to show you this. This is kind of nice. And there was another one I lost. I got to find it again. This is Geogebra. I have no idea if you guys have ever heard of that. Get this thing started. So this is kind of nifty. There it is doing the sine function. So sine is negative, then it's positive, it grows, and then it starts to shrink. And then it's negative, it grows, negative, and then it starts to shrink. So let me bring cosine in. Let me start that over again. So cosine is the x piece, so it's negative back here, and then it shrinks to 0, and then it's positive, and it shrinks to 0. Anyway, and you can see that they're offset by 90 degrees. Each one of these is a step of 90. You can see that from the scale. So let's bring in tangent. Let me clear all that crap. Yeah. Yeah. Sorry. You can add in your own sound effects. All right. And then the other thing I want to show you. I haven't put this up on, what do you call it, Canvas yet. I can eventually, someday. I also want to show you this. This is the last thing I'll show you, then we'll call it a night. I put up here, if I'm not mistaken, here. I don't know if anybody's looked at this page yet. It's got a nice filled in unit circle thing. It's got the basic definitions and how to spell those words, reciprocal identities. It's got, and then we get into stuff we haven't really talked about. There's the period, right? There's the period. There's sine, there's cosine. I have no idea why this thing I stole it from went up to 6. Don't ask me. If anybody works in music or sound design, my little brother works in sound design for plays. And he's got, you know, you got to be careful about the gain because it might clip and all this kind of stuff. So sometimes I have musicians in the class and like, oh yeah, I see that kind of thing all the time. Here's the tangent and the cotangent, and these are the really neat. I want this to make sense since that is 1 over sine. Cosecant is 1 over sine. That means when sine is 0, it goes to infinity. So it's going to go to infinity there, and it's going to go. So what happens is, if I drew that on top of this, it would just be sitting on top of that, and then this would be down here, and then there would be another cup this way. So I look at these as cups. There's a cup sitting here. There's a cup sitting down there. Hopefully you guys can actually see my mouse. This would really be, I just realized if you couldn't see my mouse. What's he talking about? All right, that's enough, guys. That's it. So that's up there on the website for you to go grab if you want to. Otherwise, that's it for tonight. Let me know if you have questions and need to hang out. Otherwise, you are free to leave. You know, or
Thank you.
Anytime. It's my job. All right. I'm out of here. See you guys.
Wait,
Oh.
I'm sorry. I wanted to talk to you.
Jasmine, yes. So what was you? Oh, the thing was, I was concerned because you turned it in so late, right?
I know. I
Now listen.
truly apologize for that. I was having an issue with my cam scanner.
Yeah.
Where it was freezing up, and I want to say it's because I have way too much space taken up by freaking photos. So I need to get rid of that so that never ever happens again, because I don't want you to think that I'm cheating for whatever reason,
Okay.
or just getting marked down because of that.
In general, whenever that kind of thing happens, you at least need to put, shoot me an email, put something. I'm finished. I'm having an issue with the app.
Okay.
Something,
Okay.
I'm gonna notice that. It's one of the first things
Right.
I look at is, because I have had issues with things like that in the past.
Right.
So I'm gonna go ahead and put the grade in there as it is.
Okay.
Did get a 90 on it. Just in the future, you have to put something. You have to give me
For
some kind of explanation when it's that long after. Yeah.
And I super duper apologize for that.
Okay.
I also was looking at, let me see if I can pull it up real quick.
Yeah.
So I understood now 4A. I totally second guessed myself on that one.
Let me see. 4A.
That, I think it was 4A. No, maybe it was 4C. 4C is the one that one of the other people brought up, and you explained it, how to do it with factoring.
Oh yeah. Okay.
I just tripped myself up because I thought it was a lot harder than what it seemed.
Oh. All right. Let me look at it. Kind of left there.
And I also didn't put my log down either. I just kind of let it go, disappear into La La Land.
4C. Oh yeah, your log just kind of left. Oh, and then you made it so gross.
Yeah,
So,
yeah, I did.
To be honest, the method you used would have worked, even though it's a lot more work. Now what should be on that side instead of 2? What should be over there? Can you see?
That.
Because how do you rewrite the logarithm so you lose it? So it's base 5.
Oh, oh man. Like, okay, you said base 5.
So 5 to the.
Oh, log 2?
No. How do you rewrite a logarithm?
Oh,
The base is 5. What's the power?
X.
No.
No?
Nope.
Oh.
What is a log always equal to? The output of a logarithm is a what? So what's log base? Listen. What's log base 3 of 9?
Oh, 2.
So the answer to a logarithm is always a what?
Power.
Power that the base needs to become the thing on the inside. So that means that 5 to the second power equals this. So this should be 25.
Oh.
So if that was 25,
okay.
everything you did would have worked.
Oh.
Yeah.
Wow. Okay.
But that's kind of a huge deal that just sort of left. Right?
Yeah. Okay. That makes sense. And then with the X value that I had, X-intercept.
Oh, down here?
Well, I thought, no, on the top, more up, more. I thought that was an X-intercept. I put X equals 6 point.
No, it's just the answer to this equation.
Oh, was that correct? No, that wasn't correct because I messed up that part up. Okay.
Yeah. Plus, notice if you put this in, 6.4, if you put it in here, wouldn't that make it input negative?
Yes.
So even if you got that answer, you have to throw it out because it makes the equation undefined. It makes the equation.
Okay. Okay, so I gotta just remember to put it back into the equation to make sure that the logarithm isn't
just like radical equations. You got to make sure that it doesn't make anything complex. Yeah. And,
okay.
Yep. I like it.
The last thing, then, so you took out the little graph that I had. Is it because, well, I kind of used it as like a basis, not as to graph it, just so I could see where I was going with it.
Oh, okay. I didn't necessarily take points off of this. I was just saying this shouldn't be something that's done. You
Okay.
shouldn't need to do this.
Okay.
Yeah.
And then I put a 3, and I think that you did put that wrong. And
Oh,
for
yeah.
the range.
All right. Now listen. Where does the asymptote start for a normal exponential?
At 0, right?
Yes. And how much is this going to get shifted up?
4. Okay, so that's what threw me off, is that I
And
flipped it.
so it should be a 4. And this is backwards because your picture shows you it should go from negative infinity up to 4.
Okay. Okay.
Yeah.
That makes sense.
All
All right. Then to find the x-intercept, I plug in 0 for the y.
Yes.
And I was trying to
Oh,
figure out how to get the x down. Should I do like the natural logarithm?
Yeah.
All right.
Yep.
I thought about that after I did it, that I should have done that, but it always tripped me up.
I just wanted a situation where you have to solve an equation, but it doesn't start off as solving an equation. So to find the x-intercept, you actually create an equation. And when you subtract 4, you divide by that negative so that it becomes positive 4 again. Then
Right, and then
look at both sides. Yeah.
right. Okay. Okay. I
There
got
you
that then.
Cool.
Awesome. Thank you so much.
You're welcome.
Have
All
a good night.
You too. See you later.
Bye-bye.